Good morning, students. Hopefully you're enjoying the nice warm weather. Everyone seems to be telling me that we need some rain. And rain is okay. I mean, I'm glad for rain too. I guess it is a little bit on the dry side, but if I can recall, once we get to the end of the term in May, we usually get monsoon season and it rains and rains and rains. So I'm sure Mother Nature will allow us to catch up with the precipitation. I can recall trying to travel to North Carolina one year, could barely get out of the airport at Intercontinental, was delayed. And then of course, trying to get into North Carolina was also delayed. So I stayed the night in Charlotte and then same old song and dance, got on a plane the next day to get to my hometown where I grew up. And I thought, well, okay, this happens. But on the way back, the same thing happened. The rain was so bad that the plane could not land again in Houston. So that was a particular year. I think this was 2016 when we had so much rain that it just planes couldn't even fly. And you normally don't think of that being much of an issue. But so I'm sure that we will catch up and we'll have the precipitation that we need. What I want to do today, this week will be the last week that we do the trigonometry. I want to complete some identities that are important that you will use in calculus. And then of course on Thursday, we will talk about solving trig equations. We've been solving equations, but now what we want to do is maybe input some of the algebra and some of the techniques that we normally think of using in college algebra to trig equations. That is, we will apply the same routines, the factoring, the zero product, all of that. But we can also use the identities, just like we use algebraic identities, we can also add the trig identities. So I think what you're going to find is that the equations are a natural extension of what we've already been doing. And of course, as you continue to take engineering classes and you take physics classes and whatever, you will see more use of equations that have the trigonometric characteristics. So again, it would be nice that you could just take a math class in trigonometry and just spread it out over the entire semester and actually have a fun time with it. But this is prep for calculus. So we're rather in an intense mode. So let's get started with that. What I want to do is to begin with some basic actually identities, not inequalities. I think we'll stay away from those right now. And if I have time later in the week, I may go ahead and do a proof of one of these addition formulas. Right now, I want to show you some of the basic ideas that we have and how these addition and subtraction formulas actually give us many more identities that's going to make our work in calculus easier. And so you see I put calculus here because you will use these just like everything we've done to this point. So the first theorem is called the addition/subtraction identities. Now, again, like I say, the proof here uses the congruent arcs are subtended by congruent chords, a very useful geometric theorem that we have utilized before. But what I want to do is state them and then use some of them and then show you how we can manipulate them to get new stuff. So we started with the unit circle and we see how everything just grew from that. So what we're going to do is take real numbers. I'm going to use, ladies and gentlemen, uppercase letters for now, just so it's very clear. Sometimes you'll see a theta and a phi or a u and a v, but I want to make sure these are very clear real numbers. So the first one will look like this. I'll just go ahead and start with the sine of a plus b. Now, the nice thing or the not so nice thing about trigonometric functions is that they're not they're not additive in the sense sine of A plus B is not sine of A plus sine of B. Wouldn't that be nice? In algebra, functions that behave like that are called homomorphisms, they're not they don't occur all of the time. And so when you have one, you're like, wow, I've got all this great algebraic structure. But in trigonometry, sine and cosine don't behave that easily. And here's what we get. We get sine A cosine B plus sine B cosine A. Now, of course, you can write these in any order you like, but usually when it comes to the sine addition formula, I like to just basically show that what's happening is that the argument is switching. That is, you get a term, which is the product of sine A and cosine B, and then the second term is the product of sine B cosine A. So the two arguments switch around. And this will form a list of identities, ladies and gentlemen, that you will use over and over and over and over. And you will basically commit these to memory. Now, not all the identities we talk about today will be so easily learned because you won't use them as much. But again, just remember, put these on a note card, have them ready for easy reference. Now, the subtraction formula is very similar. Sine of A minus B is this formula where we replace the plus with a minus. So we get the sine A cosine B term minus the sine B cosine A term. So we look at the sine addition and subtraction formulas as being very user-friendly, easy to remember, not difficult in the sense that anything is untoward here. So we've got the plus here. We also have the plus here. We see the interchange of the argument between the two expressions here. We have a minus here, we have a minus there. So we say that's user-friendly as far as committing to memory. Now the cosine is a little bit quirky because it's an even function. Cosine A plus B, and this is a very useful identity. In its oddness, it actually, well, oddness in the sense that it gives you a funny looking formula. Cosine clearly is an even function. It gives you lots of useful identities. And it looks like this. We get cosine A, cosine B, minus sine A, sine B. So this one's really very different from the sine addition and subtraction. Notice the plus here is complemented with a minus. And notice we have two expressions that contain the same trig function, but different arguments. So we have cosine A, cosine B, minus sine A, sine B. Now, some students say, well, that's easier to remember because you have the same trig function. So possibly a way to think about it. And then, of course, you would say, if we actually put in a minus sign, would we then have a plus sign in the other side of the identity? And we actually do. So we have cosine A, cosine B, plus sine A, sine B. Now, when you talk about proving these, you usually start with this one, and then you can get the other three very quickly using cofunction and just odd and even nature of the sine and cosine. So again, if I have time, I'll go ahead and go over this, but time is a little bit on the short side. So when I can work it in, I will. The main thing here is that we want to be as comfortable with these as we can. We'll do a couple of examples, but I want you to look at these as being non-trivial identities. You don't look at this and say, oh, I figured that out just by looking at it, because it's not that way. These are non-trivial in the sense that you would not think this would be the case. So the trig functions in and of themselves have some very interesting properties, and it's more complicated than the logarithms, if you can imagine that. So the main thing here is, and this is what I tell my students the first time you see these, practice writing these down. Just write them down like the inverse trig functions. Commit them to memory. And as you use them more and more and more, then they will be up here in your long-term memory. Now, the fifth and sixth one, and I'm sorry, these are for the tangent, and unfortunately, they don't get as much time in the mathematics, and it doesn't mean that they're unimportant. It's just that 1 through 4 get most of our attention. So when we think of the tangent of a sum, we get a very user-friendly formula in the form of a quotient. That is, we get tangent A plus tangent B, and then 1 minus the product of tangent A, tangent B. So again, this is easy to prove by just taking the ratio of, in this case, 1 to 3, because tangent of A plus B is just sine of A plus B divided by cosine of A plus B. So that's a very simple proof, very algebraic. And then for 6, we just do the same thing. We think of taking the ratio of sine of A minus B over cosine of A minus B. So again, what happens here is that the pluses and minuses just interchange. So students usually like this. This is not too hard to put in the memory bank. That is, we have tangent A minus tangent B divided by 1 plus tangent A, tangent B. Now, again, why is it that we focus on these? Because you can think there just must be tons of identities. The key is that these particular identities showcase particular characteristics of the trig functions that turn out to be very useful to us, especially as we study science, especially as we study engineering, and most importantly, mathematics. And so it doesn't mean that there aren't tons of other identities that you may not see as you continue your education. It's that these will come up all the time, and they will always end up on a fundamental sheet of identities. And again, it's like this. When new mathematics is created, ladies and gentlemen, basically what happens is that all the stuff that gets used gets taught over and over, and the other stuff just kind of falls into oblivion. Not that it's unimportant, it's just that the uses of it are less. And so unless you are just in a specific discipline that uses certain ideas, you wouldn't see them. Now, one thing I want to note here that's very interesting as an offshoot to this is the famous lemma, kind of like Professor Ron's lemma for the AC, and then Professor Ron's lemma for solving the basic trig equations. There's a utility here that is important in the sense that when you solve math problems, you can get the sum of a sine and a cosine function with coefficients. And it's very useful to usually put them together, because on your last test, you learned how to graph functions like sine, cosine, cosecant, et cetera, using transformations. So it's easier to combine two functions to one trig function and then apply the transformations to graph it in the simplest way. And so this is something that occurs quite a bit. So for instance, if we look at it this way, we'll say that A, B are fixed real numbers, fixed in R. Then for X, a real number, we have a way of combining things, and we're going to actually think of A comma B as a point in the plane, and it looks like this. And you look at this, the first time I ever saw this was in a differential equations class as an undergraduate, and now Dr. Stewart actually puts it in his textbook, and others have done the same as a way of introducing this before you get to calculus. So you say sine A times sine of X plus B. So you got this coefficient times the sine function, and you have this coefficient times the cosine function. And it has a very Pythagorean equality on the other side with one of these functions here. It looks like this: A squared plus B squared times sine of X plus phi. Okay, so again, graphing something like this, you know how to do. So we would rather look at this graph than try to do it this way by adding functions, which can be a little bit uneasy. So we're thinking, where did this phi come from? Well, the idea is that if it makes sense, it would say that tangent of phi, we think of this as a right triangle, opposite over adjacent. So this is why this is such a nice result, because it appeals to our right triangle interpretation. Tangent of phi would be b over a. Now, the important part about this is that if we think of a comma b as a fixed point in the plane, then the phi here needs to represent the appropriate angle from the positive x-axis. So for instance, like if we're solving an equation, we might use the inverse trig functions and we'll find that, okay, the inverse trig function gives us a solution in the fourth quadrant. And maybe we're gonna have to amend that by adding a multiple of the period to basically push it into the appropriate quadrant. Because again, this basically has to mean that, for instance, a comma b element of some quadrant, we'll just say in this, I'll just say this. Let me do it with a comma here. As a point and also as an angle, these must terminate, and I say terminate with quotes, in the same quadrant. So you can think of this as being a point on the unit circle, as though it's not really. So for instance, here's an example. If we had the point, say, -2, 3, this is in the second quadrant, then this would mean that our expression for phi must also live there, so that we get a correct rendering of this formula. That's the only catch of it. So again, we think of when we work with points in the plane and we think of our reference triangle, we say, okay, well, in the third quadrant, the cosine and the sine are both negative. So we would have to say, okay, our cosine would be less than 0 and our sine would be less than 0. But then, of course, the ratio of sine to cosine would be positive. So again, this is the same mechanism at work. So again, just like I've said, when we deal with the law of sines and we see those basic sine equations, we have to think, okay, where's another solution? Well, there's another one in the second quadrant. Does it make a second triangle? So the same ideas are coming back over and over. So this is what I'm talking about when it comes to the arithmetic of the unit circle. We're kind of haunted by it because it'd be nice if we could just cruise right on through and just, throw caution to the wind, but we can't. So let me do a couple of examples with these. Now, look at these new guys right now as just ways to do computations. For instance, if you take an A and a B that are already on the unit circle, you can make combinations here to get other exact values. So this basically broadens what we can do in terms of exact values, but it doesn't mean we're going to add new points to the unit circle. We're fine with the unit circle. It has what we need. And if it were more cluttered, we wouldn't be able to write it down anyway. So let's do a couple of examples. So this lemma here, I want you to put this on a note card and put it in a red box, okay? Because this is a very, very useful result. And here's the thing, ladies and gentlemen, you will use this when you least expect. So when you get the differential equations and you're thinking, why does the answer look like this? Oh, this is this, and so we get this, all right? So sad part about trig is that you learn all this stuff and then you're not always sure when you're going to have to use it. But some point in calculus 1, 2, or 3, you're going to be using these ideas. Unfortunately, it doesn't come all at once. So you have to keep things percolating. Now, the first thing I want to do is, since I've already been talking about this, I made up an example. with this lemma. I'll do the lemma first, and then I'll go back and do one of the addition formulas. So here's an example with the lemma. So again, I made this to have horrible numbers just so you could appreciate this. So we want to write the expression as a single sign expression. So we're going to have a sum that we're going to put together. So here's what we have. I just made this up. -2 sine x minus 5 cosine x. So we're going to say, what does this equal? Well, this is where we get to use the lemma. Say you've solved an equation, say you're in a physics class and you solved an elementary differential equation, and you got this as the answer. And you look, you know, your professor says, okay, here's some solutions, and you see a nice graph, and it's like, well, I don't think I got that. And then you're thinking, oh, this is like logarithms. You combine things in a certain way and you get an answer that looks very different. So this is a case of that. So this is going to be use lemma. So just to remind you, A sine x plus B cosine x will be the square root of A squared plus B squared times sine, again, kind of long-winded, plus phi, where tangent of phi equals B over A. Okay, so this is something that you really do need to have on a note card and practice. It's not going to stick with you, but if you write it down a couple of times and think of the triangles, it will be more of your long-term memory as time ensues. So now we can see here A equals -2 and B equals -5. So ladies and gentlemen, if we think of an ordered pair here, -2, -5. This is in the third quadrant. Now this is Professor Ron talking here. I seldom look at anything in the book without putting my own signature on it, because as a mathematician, you need to understand why things work. I mean, the idea is that when you work a problem, you don't want to be like, well, I wonder if this is right. I don't teach that way, and I don't expect you to learn that way. Is it easy? Absolutely not, but it will guide you correctly. So now you're thinking, all right, well, this is in the third quadrant, so whatever I get here, I will need to make sure that phi terminates in the third quadrant by adding a particular multiple, say a multiple of the period of pi, and we know that smallest pi period for pi is pi. You know, 2 pi is a period, 3 pi is a period, but those are multiples of pi. Just like we have cosine 2 pi, 4 pi, 6 pi, etc. So when we look at this, we say a squared plus b squared. Again, we squared the -2, we get a 4. We squared the -5 and we get a 25. So this gives us a 29. So this implies square root a squared plus b squared equals the square root of 29. So we filled in that part right there. So we're just kind of writing down everything that we're going to need. And then of course, we're going to say tangent of phi, and of course this is not on the unit circle, is b over a. So this is -5 divided by -2, which is 5/2. Okay, so equivalently, again, this is a positive number, so we know that this particular value solution will be in the first quadrant, because we know that the inverse tangent runs from -pi/2 to pi/2. How many times have we written that down? It's like, by now, that should be something that just kind of pounds in your head. So this says that phi is the actual inverse tangent of 5/2. And then of course, this is a positive number, so this is in the first quadrant, okay? So if we look here, we're thinking, okay, we're going to have to add a multiple of pi, or in terms of degrees, we have to add what? 180 degrees to push this into the third quadrant. So like I said before, it must be the case that these two objects terminate in the same quadrant for this to make any sense. So now this will imply use. So this is kind of like the phi in quotes. It's not quite what we need. We need to push it to the third quadrant. So we're going to have inverse tangent 5/2 plus pi, which is now in the third quadrant. And that's what we need since our point is in the third quadrant. That is essentially they terminate in the same quadrant. So now this implies that -2 sine x minus 5 cosine x equals, so we have the square root of 29, fill this in, sine x, and then our phi is all of this, plus inverse tangent 5/2 plus pi. Now, one thing that we like to do, we love our degrees, don't we? We just love degree mode, especially when we're working with the triangles. So if you wanted, you could actually write this in terms of degrees and write it in degree mode. So for instance, here we could say inverse tangent of 5/2 plus pi, and then convert it to degrees by multiplying by 180 degrees divided by pi. And then, of course, by Google, of course, we're just doing this ourselves. You'll get approximately 248.2 degrees. Again, this lies in the third quadrant. So again, if you wanted to replace this with this by thinking of degree mode, that would be fine. Maybe your physics problem would be more suitable if you use the degree measure. Now, of course, we don't want to put the approximation in here. We want to put the actual value, the exact value, so later on we can approximate if necessary. So I wanted, now, of course, in the WebAssign or whatever, you might have some nicer numbers here that turn out to be nice unit circle angles, so that'll be good too. But I want you to appreciate this for the fact that now we have one sine function here that can be horizontally shifted and then, of course, vertically stretched here. And that we can actually get a reasonable graph of. This would be harder to do. So having the single sine function is much more useful. And when you solve your second order linear differential equations with constant coefficients, and of course you'll have a right-hand side which is either 0 or non-zero. That's when you solve the homogeneous equation and the non-homogeneous. And what you'll figure out is that the general solution will just be sums of those, constant multiple sums of those. So the key here is that to do the calculus, you have to know the trig. And so this is going to be a nice step in doing that. I hope that now you see how we use everything that we've been working on previous to this and how it all comes together. This is the important thing. Now, so enjoy this. This is fun. I always thought it was interesting to have new tricks, so to speak, to be able to push problems forward. Now, what I want to do is just look at a very simple example. I want to also remind you that as you use a different identity, values are going to look different. You're going to have some square roots hanging out, and you're going to say, that doesn't look like that equals that. But in many cases, depending on identities that you use, ladies and gentlemen, the actual responses are going to look very different. And that's just the nature of trig functions. So for instance, say we're interested in figuring out a value that's not on the unit circle, but it is comprised by combining values that we already know. So for instance, we could say compute the exact value of, and I'll write this down, cosine of 11 pi over 2. And of course, as we do the half angle formulas over 12, as we do the half angle formulas, you're going to think of another simpler way to do this. But I want to use the addition formula. So what we want to do is partition 11 so that we can actually write 11 pi over 12 as a sum of radian measures that are on the unit circle. So first we observe, when you partition an integer, you simply write it as the sum of two integers that are positive. So for instance, in this case, 11 can be written as 3 plus 8. Now you're thinking, that's earth-shattering, Professor Ron. But here's the key, ladies and gentlemen. If we want to rewrite this as a sum of two radian measures that we know something about, we have to be very careful. You could use other combinations, but they're not going to be on the unit circle. So this implies that 11 pi over 12 is just 3 pi plus 8 pi over 12. And then, of course, 3 over 12, that'll give us 1/4, so we get pi over 4. And then 8 over 3, 8 over 12 will give us 2 over 3, or 2 pi over 3. And these are values that we know a lot about. These are on the unit circle. These are radian measures that we know quite a bit about. This equivalent to 120 degrees, this equivalent to 45 degrees. So we'll just say radian measure found on S1. So again, you're thinking, well, we're just going to add all these new coordinates to the unit circle. No, it just now, with the way we manipulated things and introduced new identities, we have the luxury of being able to get some exact values and, less use of the Google calculator, even though we still love to use it. So now we can say, let's use our identity. So recall cosine A plus B. So since we have a sum here, we'll do the sum here. Remember, this is cosine A, cosine B, minus sine A, sine B. And you're thinking, here we go again, just substituting numbers, working with the arithmetic of the unit circle. So now let's go ahead and fill everything in. So if you like, to the side, just write A equals pi over 4, and it's your choice. It doesn't matter how you assign them. Of course, that won't make any difference. And B equals 2 pi over 3. So this implies, or if and only if, cosine of 11 pi over 12 is cosine of pi over 4 plus 2 pi over 3. And now let's just go ahead and fill it in. So again, let me just mark this off. This is A, this is B. Lots of bookkeeping. So we get cosine of pi over 4, cosine of 2 pi over 3. Now minus, following the identity, sine of pi over 4. Use parentheses if you need, just to make it a little bit clearer, and then sine of 2 pi over 3. So now let's just go ahead and do our little unit circle. Remember, at 2 pi over 3, we have, and this is always interesting when we think about how we do these. We have the coordinate pair -1/2 root 3 over 2, the cosine and the sine. And then for the pi over 4, we have the 1 over root 2, 1 over root 2. Okay, so that just gives us what we have to fill in. So now cosine of pi over 4 is 1 divided by root 2. Cosine of 2 pi over 3 is -1/2. Sine of pi over 4 is 1 over root 2. And then, of course, sine of 2 pi over 3 is the square root of 3 over 2. So again, you can think of these as reference angles if you want, but sometimes it's just easier just to write down the actual coordinate pair. You have all this flexibility at your disposal. And since we have to kind of use everything, it probably makes more sense just to focus on this to make sure the signs are correct. So now notice we have -1 over 2 root 2. And here we have a minus, so we have minus √3 over 2 root 2. Of course, we have the same denominator, so this will be a negative. Just go ahead and factor the negative, put it on to the left here, 2 root 2, and then 1 plus square root 3. And of course, if you want to, you could rationalize this and get rid of the square root in the denominator, but this is more than sufficient. So the idea here is that now, of course, this is an exact value of cosine of 11 pi over 12. And again, let me just also reiterate that if you use a different identity, this may look a whole lot different, but be exactly equivalent. Lots of times when you have radicals and things, ladies and gentlemen, you can just square both of them and show that the value you get is equal. That's a good way to show that things are equivalent, especially when you've got lots of radicals running around and it doesn't appear that they're equal, at least face value wise. So when it comes to doing these, this is what's so good about practice. You practice the new identities, just substituting values that you already know to get new results, so to speak. So we just rehash what we already know to discover new values, so to speak. Now, what I want to do is say if we've got all of this, again, you could use the sum formula for tangent, but I've got a nice little algebraic expression now that we can use just like we did on the test. Now that we have the sum and addition formulas, we can apply the same technique to these expressions. So here's an example. So I'll say write as an algebraic expression. So I'll just say write the composition as an algebraic expression, just like you did on the test. So in this case, we have the following. That is kind of naked how these come out. We have sine of the inverse tangent of x minus the inverse tangent of y. Now, when you look at this, ladies and gentlemen, you're thinking that if it just stopped with that, that's what you've been doing. But now that you have the difference formula for sine, there's nothing that's going to keep you from being able to do an algebraic expression. It's just now you have two triangles. So before you just had one triangle, now you have two. And of course, you can do these all with Pythagorean identities, but I would be the first to say the triangles are very user friendly. And as long as you keep up with the signs, there's no problem with it. So here's how we can do. We proceed the same way. That is, we can just say that theta equals inverse tangent of x. Just use your favorite letter, theta, phi, whatever. And we can say phi is inverse tangent of y. And of course, these live between negative pi over 2 and pi over 2. Same here. So equivalently, say same song and dance. We've done this a million times. So tangent of theta is x over 1. Just write it as a ratio. We choose this because it's easy. And then tangent of phi is just what? Y over 1. So now we can see that we don't have to learn any new techniques. We just have a new identity, so we can apply the old technique to the new identity. So now we can draw triangles, again, the lazy method and the good method, so to speak. So we just have what? Opposite over adjacent, so x over 1. And then, of course, Pythagorean identity, 1 plus x squared. Of course, 1 squared being 1. And then, of course, here, the same thing. Do your reference triangle. So we have a phi. Again, opposite over adjacent, y over 1, and then the square root of 1 plus y squared. So again, same technique, an additional triangle. So we can now write and use our identity. This will be sine of theta minus phi. Again, use whatever letters you like. Maybe you want to use an uppercase A and an uppercase B like I did in the identities. It is completely your choice. So now let's go ahead and write this down based upon the identity. So this is sine theta, cosine phi. Now remember, the minus here puts the minus here, and then the arguments flip, sine of phi, cosine theta. So you have to admit this is easy if we just accept our new identities, but there's more stuff. So there's extra stuff to do, but the technique is the same, essentially the same. So now we can run to each triangle to compute each of these trig functions. So sine theta, we go to the theta triangle. This will be opposite over hypotenuse. So we get x divided by the square root of 1 plus x squared, okay? So that, check it off, all right? So now we need cosine of phi. So let's go to the phi triangle. We need what? Adjacent over hypotenuse. So this will be 1 divided by the square root of 1 plus y squared. It's amazing that we can do all of this interesting mathematics before we even get to calculus. So what we're finding, ladies and gentlemen, is that the calculus requires all of this, and this can be just as challenging. So check. Now, when we look at this, we say, okay, let's go to the phi triangle here to do the sine. So we have opposite over hypotenuse. So we have y divided by the square root of 1 plus y squared. And then cosine of theta, go to the theta triangle, adjacent over hypotenuse. So we have 1 over the square root of 1 plus x squared. So now, well, the trig people have been good to us because we got the same denominator, so we just have x minus y. So we're not gonna quibble about that. So we have the square root of 1 plus x squared times the square root of 1 plus y squared, and then of course x minus y. So actually no more difficult than what we've been doing. What I want to focus on, or at least mention here, is that if you do problems and these are replaced with x and y with numbers, the same technique ensues. You have numbers here on the triangles. So there's no difference. So the key here is that with the new identities, we use the same tried and true techniques. We love the triangles, the ratios of the sides, so convenient, so convenient. And so you can apply this to any setup, especially what's nice here. We like the fact that with the inverse trig functions being the inner functions, that opens the door to the triangle. And then of course, we might have a particular angle that's described in terms of a trig function, which will still allow you to draw a triangle. So the techniques will not change. And what's nice about this is that what we're doing is not really adding any new theory to the trigonometry. We're simply taking what we know and extending it. And isn't that what we do in mathematics? Isn't that what you do in science class? Isn't that what you do in English or anything that you do? You take the basic concepts and extend them to solve even more interesting problems. So, okay, so we've got these new identities and we're thinking, all right, we can combine them with what we already know to produce some new structures. Now what we want to do is take these new identities and just recast them over and over. And this is what I'm talking about, even more so than we did primarily. We're going to start with the basic identities and create even new identities. So this is the next thing that we're going to do, create new identities using the addition and subtraction formulas. So you can say addition and difference or whatever, your call. Sometimes we say sum and difference. Sometimes we say addition and subtraction. So you could say the sum referring to A plus B. You can think of difference referring to A minus B. Your choice. They all say the same thing. In one way, you know, it it matters not to me. It just what only thing that matters to me is that your work is correct. Okay. I do not care if your work does not mimic the way I do it. You must do it, however, correctly. So don't get mad at Professor Ron when I note that there are errors in your work. Okay, that's how you learn. And do I have high standards? Absolutely, I have high standards because the school has high standards. Why do I teach at San Jacinto College? Because the philosophy of the academic environment is extremely high. Our successful students go on and complete their degrees. And it is not easy. It will never be easy. I'm just, again, work to do good work, to own what you do, and to grow. That's all I want for any of you. Now that we've gotten that off our chest and we're thinking, okay, what are we going to do, Professor Ron? Let me do this. Let me go ahead and write down the ingredients here. You're thinking, oh, here we go again. Let's write these down so I can refer to them. And then sometimes I'm just going to come back to them and say, okay, kids, here's the list again. Let's use it. So let's remind ourselves what these are. We have sine. Oh, well, let me do it this way. Let me not put so many parentheses because I'm going to be super lazy. Allow me to be a little bit lazy, ladies and gentlemen. Sine A cosine B plus sine B cosine A. So we're going to do the double angle formula. So I'm going to write down the identity that I'm going to use to get a double angle formula. So the first here, I'm just take your red pen and say double angle. Double angle. Sometimes the professors will say, when I was an undergraduate, the formula of the double angle, and we thought, boy, that sounds really fancy, but we knew what it was, double angle formulas. So what we're going to do here is we're going to replace B with A. So we're going to say sine of A plus A. So again, replace B with A. Now, what's A plus A? That's 2A. That's the double angle. The double angle. How funny. We've got all this new stuff. Sine of the double angle. So you're thinking, wow, we got that for free. Just replace B with A. And so we get sine of A plus A, which is sine of 2A. You're thinking, well, who cares? Well, we do care because look what it's going to do. Now we're going to get sine A cosine A. So this is sine A cosine A. I need to do these because you clearly won't believe me. I think you believe this because I couldn't make that up. And then of course here, the B is A, so we get sine A cosine A. Well, we get two of the same. We get two copies of sine A cosine A. So this is 2 sine A cosine A. So let's just kind of summarize it. Sine of the double angle. And you will use this, you'd be surprised how much you're going to use this even in Calculus 1. Sine of the double angle. So sine of 2A is 2 sine A cosine A. That kind of rolls off the tongue. So now, if you're going to remember this, you need to know this. So basically these addition and subtraction formulas are going to give us all these new ideas, every one of them. So repeat after me: sine of the double angle. Sine of 2a equals 2 sine a cosine a. So you're thinking, if you were doing a physics problem, say you had something like this, you had 2 sine x cosine x dx. So you had this, say you had this particular integrand in calculus. You're going to think, that's going to take me time to do. I'm going to rewrite this with the double angle. Sine of 2x dx. And that's an easier integral. So you're going to find, this is kind of like a little aside where you're going to find uses for these nice trig identities. Because once you learn the calculus, you're going to say, oh, that's going to be easy to do that. That's more challenging. That's simple. Once you learn the calculus, you're going to see that these identities are very, very useful. Now, let's not stop with sine. Let's do cosine of the double angle. So let's write down the cosine. So a plus b cosine a. Oh, and of course they repeat, don't they? Cosine, cosine. And then that pesky minus that we don't expect, sine A, sine B. Now let's do the same thing again. Let's replace B with A like we did here. So we get cosine of A plus A. So what do we say? Cosine of the double angle. So now we just go up here and say, okay, so this is cosine A, cosine A. Of course, B has been replaced with A, so we get sine A, sine A. So that's just cosine squared minus sine squared. It's almost the fundamental identity, but not quite. Got that pesky minus. Okay, so you're thinking, well, this one looks a lot more useful than that, Professor Ron. That's got a cosine and a sine in it. That's not very helpful. So we're going to fix it. Okay, so let's summarize. We're going to say cosine of the double angle can be written as the difference of two squares, cosine squared A minus sine squared A. Now here's the trick. Let's also say, if we replace cosine squared with 1 minus sine squared, that's going to give us a 1 here and 2 copies of the sine. So we can do 1 minus 2. This is great when we're solving trig equations. So this is basically saying cosine squared A equals 1 minus sine squared A. So if we do that replacement, we get a formula that only has the sine term in it. That's an improvement. And now, of course, there's no need to discriminate. Let's do the same here. Let's replace sine squared A with 1 minus cosine squared A. So you're thinking, this is so simple. Why do we care? Well, these just turn out to be very useful. So this is going to give us 2 copies of the cosine squared, but since we have the minus here, we get the 2 up front. So we get 2 cosine squared A minus 1. So we get 3 formulas out of 1. So when we have the cosine of the double angle, if we're solving a trig equation, we're going to enjoy the second one and the third one because it will just have one type of trig function. For instance, if we're solving a trig equation, we want all the trig formulas to be the same, like having all the bases the same with the logarithms. We can't apply the algebra if we've got all kinds of different trig functions hanging out. We gotta replace them so we can, like have an x and an x squared. We can work with that. So we will find this to be very useful when we're working with equations. So again, the cosine of the double angle has 3 forms. Put these on a note card, put them in your memory bank. Very, very useful. So we're like, okay, so again, double angle. Now you're thinking tangent, are we going to leave tangent out again? No, we'll go ahead and throw it in. So just remember, tangent, this is quick, but A plus B, we'll just write it down. This is tangent A plus tangent B divided by 1 minus tan A tan B. So again, just like with the starting out with these, we can use these and now we can rehash them. So now replace B with A. So we get A plus A, and this is tangent of the double angle. No, the thing is, the tangent's not a bad dude. This is okay. We just don't use it as much. The calculus is not as useful here. It really, when you learn the calculus, sine and cosine, you're going to see why some of these trig identities are so useful. The tangent doesn't have as nice a calculus as sine and cosine. It's much more complicated. So the thing is that we it's not that we don't want to use this much, we just don't get as many opportunities. So now we'll have tangent of A plus tangent of A. And then we have 1 minus tangent A times tangent A. You're thinking that's kind of boring. So that gives us 2 copies of tangent A, 2 tan A. And then downstairs, 1 minus tangent squared. So this one, you know, it's useful, but we just don't get as much use for it as we do these two, okay? So again, as you need these formulas, don't worry about maybe memorizing all of these. You will learn these because you'll use them a lot. But if you commit this, this, and this, the addition, put these up here, you can always get these. So we're thinking of this basic list right here as being fundamental. We know that basic list of the addition and subtraction, and we can get all these new guys very simply, just by making a change of variable, okay? Change the variable. You know, when you're doing math, you can use whatever variables you want and rederive equations and do whatever you need to do to finish the problem, as long as it's legitimate mathematics. So now, let's take these equations. You're thinking, is there another way to take these double angle formulas and get some really useful stuff? Yes. The next will be called the power reducing. And this is going to use the cosine of the double angle. Like I said before, when we're doing the calculus, integrating even powers of cosine and sine, not a lot of fun. So we need a way to reduce the power. So here's what we're going to do in this particular case. We know the following. That is, cosine of the double angle equals, let's write the first one we came up with. What was it? 1 minus 2 sine squared A, right? That's a square, that's a first power. So let's rearrange it to write sine squared as a first power of cosine. So equivalently, take this over and take that over. So we have 2 sine squared. I want to do these derivations because they're important. Otherwise, you're not going to believe me. The same old thing as I said before. And now divide by 2. So you can put the parentheses in or leave them out. 2a is usually pretty clear. So this is what we call power reduce. Write sine squared as a first power of cosine, power reducing. Why is this useful? Integration. Complicated to integrate, easy. Okay, power reducing. This complements the calculus. We're thinking the logarithmic identities complement solving equations that contain logarithms. Why? Because we can take logarithms and combine them, okay? Again, the calculus of sine and cosine, very nice. This is very helpful right here. Now let's not stop with this. Let's go to the double angle formula that uses the cosine. We know now all these formulas, put them on a note card, practice writing them down every day. Write them down. You wake up in the morning, write them down. Get to the middle of the day, write them down. Do study for 3 hours. Then go to bed, write them down. Tell everybody in the family, these are important identities. Have everybody talking the identities. And then you're thinking, there's no way you can escape this. It'll just be something you're thinking about all the time. So now cosine of 2a, let's do the cosine one. We've got 2 cosine squared a minus 1. That was cosine of the double angle. Now, of course, let's just solve for the square. And we don't, it's easy to do. We're just going to take the 1 over. So equivalently, 2 cosine squared a equals 1 plus cosine of the double angle. And then we can divide by 2, and you're thinking, these look the same, except for a sign. Amazing. These are your friends, okay? We write cosine squared as a first power of cosine, power reducing. I cannot tell you how important these are. And when you do reduction formulas with integration by parts, you use these. You use the Pythagorean identities. Why do we talk about Pythagorean identities? Well, they form the cornerstone of the right triangle, and boom, they're in our face all the time. These are important. And what's nice about calculus is that you always have options. You don't have to do a problem a particular way. You get to pick, okay? You get to pick. Again, math is flexible, but you have to respect the particular support that you use. Make sure that you respect the mathematics to move the problem through. Now, so you're thinking, okay, so the interesting thing here, and this is a very important construct, so to speak. Again, I'm just going to write this useful in calculus. So what is this class? Pre-calculus. So we're going to cover the trig that you're going to use in calculus. I know I keep saying the same thing over and over, but I just want you to remember that that's what we're doing in this class. We're preparing you for the calculus. Now, and we'll do an example of these, but I want to go ahead and get out the half angle formulas, and then we'll do a couple of examples. But I want to make sure that you've got all these formulas first. Now, the next will be the half angle. You're thinking we've got the double angle. From the double angle, we got the power reducing. So now what we're going to do, we're going to take the power reducing and do some algebra. So here's the deal. We're going to let, in this case, A be a half angle, U divided by 2. I've got to change the variable, so I'm just going to use U over 2. So this is half angle, half angle. So then, if we look at the power reducing, we'll say, okay, so notice, what does this say? 2A equals U, right? If A is U over 2, 2A is U. So let's go back to our power reducing. So let me just write down what we know. Again, I do want you to believe me. We know, in this particular case, that sine squared of A equals 1 minus cosine 2A divided by 2. So now we're going to do a transformation. we're going to replace a with u over 2. So sine squared of u over 2 equals 1 minus cosine. 2a is now u, so you can just do u if you want. I'll do like that. The u over 2 is kind of clear that that's an argument, but let's just want to be clear that that u doesn't run into the s. You get that? So now we can solve for sine of the half angle by using the square root property. And you're thinking, oh, this is a lousy formula, plus or minus. We've got to figure out which sign to use. So sine of the half angle will be plus or minus the square root of 1 minus cosine u divided by 2. So we put the 1/2 out here. So this is, we're like, not the best, but we'll do. So the key here is if you use the half angle formula, first you have to figure out where u over 2 terminates, just like we've done before, and that will select the sign here, okay? And then you substitute into here and you're good to go. So again, you're thinking when we did 11 pi over 12, if we have a cosine half angle, we could do 11 pi over 6 divided by 2 and get an equivalent answer that won't look like the one we just computed. So we'll always have flexibility here. Now, let's do write down again what we know. We know cosine squared A equals 1 plus cosine of the double angle divided by 2. You can spend time deriving these every day just to remind yourself, and then before too long you can tutor it. You'll know it. So now let's do the substitution. A we replace with u over 2, so a nice change of variables. Cosine squared of the half angle will be 1 plus cosine of u. And now, just like we did here, we'll apply the square root property. So if and only if cosine of the half angle will be plus or minus the square root of 1 plus cosine of u divided by 2. So again, you look at this and say, well, this isn't the best. This plus and minus, that's the best we can do. Sometimes we like the quadratic formula. It's got plus or minus in it. So we're kind of stuck with these. Again, if you use this formula, you figure out where u divided by 2, the half angle terminates. That will allow you to pick the sign. There's no guesswork here. That's why I keep saying that we started with the unit circle to establish the what? To establish the what? The arithmetic, okay? So the last part is, it's like, and this is what I mentioned, because when we did one of the identities in 7.1, I said, this is the half angle formula for tangent. And I said, ladies and gentlemen, you see there's no plus or minus in this. It's like a formula that's like, wow, how did we get this? This can't be. So let's do it. So for tangent, that is, we need a formula, and this turns out to be useful in Cal 2, for tangent of the half angle. And I use, u over 2 is what I used here. Okay, so let's do that. And I'll show you some algebraic manipulations that will allow us to get this very easily. So first, we can say, in this case, we'll use the double angle. Sine of u will be 2 sine of u over 2 cosine u over 2. So this is sine of the double angle, where we've just replaced 2a with u, and then of course the a just is u over 2, just like we did before. And this is where we use one of the alternate forms for the cosine. Cosine u equals 2 cosine squared u over 2 minus 1. So just using the same change of variables that we had before, using the double angle formulas for sine and cosine. Now, when we look at this, we're thinking, okay, how is this going to help us out? So note here, if and only if, we can do one little modification here. 2 cosine squared u over 2 is 1 plus cosine u. Just go ahead and add 1 to both sides, all right? So let's see what we get. Now, we're going to take some ratios. We're going to look at the ratio of this expression to this expression. So 2 sine u over 2 cosine u over 2 divided by this. We see what they equal, 2 cosine squared u over 2. This is kind of a very unique approach that gives you a formula without radicals in it. So note, we have this, and we have this, just using the double angle formulas with the same change of variable. And now, note what we have here. The 2's absorb, and I'm going to go ahead and write this out in another line. This will be sine of u over 2, cosine u over 2. And then we've got 2 copies of the cosine u over 2, so I'm going to write them out separately. And they also absorb. So now you can see the method to the madness here. This is just sine of u over 2 divided by cosine of u over 2. By definition, that's tangent of u over 2. But what does that equal? Well, this equals what? Sine u. This equals 1 plus cosine u. And there we have it. That is one of the more remarkable formulas in trigonometry. This is remarkable. And this is the basis for the Weierstrass substitution. In calculus 2. So again, when you see this again, at least you'll say, oh, I remember that from pre-cal. So what's nice about this is that we can use the same setup here. We can use, for instance, like if we've got pi over 4, we know that really well. That's on the unit circle. So we could divide that by 2. Pi over 4 divided by 2 is pi over 8. Get an exact value for tangent of pi over 8. You see, that's the same setup. And we're thinking, amazing. We're getting all these exact values just for free. So here's a simple example of this. So for instance, if we wanted tangent of pi over 8, this is so easy, I don't even have to do it, but I'm going to do it. Look, this is just tangent. You're thinking, I don't know this, Professor Ron. Let me use Google. So let's do an exact value. Exact value. Well, let's rewrite it using our newfound friend here. This will be pi over 4 divided by 2. Here is the u. This is the half angle formula. But pi over 4 is our friend. So we can just substitute. This will be sine, and we don't even have the plus or minus. It's built in. Amazing. So we have sine of pi over 4. And then we have 1 plus cosine of pi over 4. We're like, this is just too easy. So like I said before, we can use the new identities to get some values. So we're thinking this was worth all of the trouble because this is so simple. And then of course you could conjugate this to get another form, but since this is the calculus one, we'll just focus on it. So this is 1 divided by root 2. And then 1 plus 1 divided by root 2. Now that's a little bit messy. It's complex. So let's go ahead and get a common denominator. So we'll do 1 over root 2. You know, we do have some standards, right? So we'll have root 2. So a common denominator, root 2 plus a 1. And of course, the root 2 is absorbed, and we just get 1 divided by root 2 plus 1. And that's the exact value for tangent of pi over 8. So you're thinking, yeah, not a big deal. True, it's not a big deal. But the thing is that this will help you with the calculus. For now, doing these kinds of examples at least give you some use of it. For instance, we can't use these identities to do calculus. Not right now. Okay, I give you the idea that, okay, we will use these in calculus. But the key here is that by practicing with these types of very simple calculations, you can gain some familiarity with these new constructions. And that's all I want for you right now. I remember I had a previous boss, Professor Wilson. She says, just make sure that the students are aware of these, Professor Ron. I said, yes, ma'am. This is when I first started. And she said, they will not like these. They will find these very awkward. And I said, I agree with you. I said, it's going to be a challenge, but I completely agree with her. I'm trying to set up with this in a way so that you know they exist, that you know how to use them at least on a level that's pertinent to pre-cal. And then when you see them again, it won't be the first time. We always dislike the fact that we have to begin at square one. If we're in a science class, it's like, oh my gosh, I don't even know how to work with this because I don't know this. And that's just very uncomfortable. So what we try to do here is make you aware of this before somebody just tosses all of this on you and you feel overwhelmed. Now, we've got two more sets of identities that will again be used in the calculus sequence. One set more than the other. And I'm going to show you how to get these. So the next set will be the product to sum. You're thinking, who came up with all these? Product to sum. And then, of course, you know what I'm going to say. These will be useful in calculus. So again, we are very biased here. We're biased because we're looking at the identities that you're going to need to use in the calculus. So how are we going to do this? We're going to do the same thing we did before. Let's go ahead and write down the raw materials, sine of A plus B, otherwise you won't believe me, equals sine A cosine B plus sine B cosine A. We're going to do some linear combinations of these equations to produce the product to sum. Sine A minus B equals sine A cosine B. And then, of course, we have the minus sine B cosine A. You're probably already getting good at knowing these by now. I've written them down so much. Again, when you go back through this lecture, teach yourself. Just go through the same routine each time. It will get easier each time you do it. And then we have cosine of A plus B is cosine A cosine B minus sine A sine B. So this is what I'm telling you. Even if you forget the product to sum formulas, you can always remember these and resurrect whatever you need without having to guess. And then there'll be times when you've got all of these committed to memory. You've used them so much of late and you're like, I got it. Then 2 weeks passes and they just turn to dust. So don't be hard on yourself. Just remember, like when you study math, if you let 2 or 3 days go past after you mastered a difficult problem, you need to rework it because you won't remember it. So now the idea here is we want an identity that takes a product of trig functions and writes it as a sum. Okay, so we're thinking that again will be a very useful construct in calculus because integrating products of trig functions is complicated. Sums, much easier. So the first thing we're going to do, and let me just 1, 2, 3, 4. This is, I'm being lazy, but I don't want to write them down again. So the first thing we're going to do is we're going to add, we're going to say 1 plus 2. And the answer is not 3. I'm just saying we're adding equations 1 and 2. So we do a visual. Look, these will absorb. When we add the first two equations, these absorb. This will give us 2 copies. So this will mean 2 sine A cosine B equals sine A plus B plus sine A minus B. Now, when you do all of this, you're thinking, Professor Ron, thank you for using uppercase A and B. U's and B's look the same. Phi and theta, after a while, they start to look the same. So I'm trying to make it sure that you see what these are. I had to use the U before because I needed another letter. So hopefully that's okay. But now you can see sine of A times cosine B can be represented as half this sum. So here's our first one. The product of sine A and cosine B can now be represented as 1/2 sine A plus B plus sine A minus B. Right there. Okay, so again, you know the A and the B, you substitute them in here and use the odd nature of sine. So whatever A and B are, you sum them, you subtract them, you're done. Multiply by 1/2. So you're thinking, wow, it's this easy. So product to sum, product to sum. Difficult, easy when it comes to integrals. That's why we talk about these in pre-calc. Okay, now we're thinking, all right, well, do I need to worry about another one? Well, I'm going to go ahead and write the other one down just because it ends up in the list, even though it seems a little bit redundant. I could just flip these around and replace cosine. For instance, here, if you like, just replace B with A and A with B. Can we do that? Let's do it. Let's do it. So let's get a free one and just forget this for now. So now we could say cosine A sine B. What's that going to be? Just replace A with B and B with A. Just be cheap here. We don't care. Just go cheap. So we have 1/2. So we're going to get sine. Okay, A plus B, B plus A, no difference. That's still A plus B. Plus, and now we're going to have sine of B minus A. Okay. Now we don't want our formula to look like that. So we're going to factor a negative. So we're going to get 1/2 sine A plus B plus sine of the negative of A minus B. This is just, okay, let's factor the negative and so we can keep the same order because we want our formulas to look beautiful. Okay, now sine is what? Odd, so the negative will factor. So if and only if. So you're thinking, this is kind of a waste of time, Professor Ron. I don't need this. I can just use that formula. And I agree with you, but you're going to see this in the tables. So I want you to see where it comes from. So this will be 1/2 sine A plus B minus sine A minus B. So again, let me just go ahead and put these in boxes. Not something that's just going to roll off your tongue. You see, these you will remember. These, not so much, not so much. So usually, when students are working these, they'll write these equations down to get the sum, just doing the linear combinations like we've done, adding or subtracting, and then boom, they fall right out. And then of course here, just replace A with B and B with A and use the fact that the sign is odd. Of course, you had to use that on the test. That was one thing where I deducted points if you didn't use the fact that the sine function was odd in that interesting problem that really was very simple. Again, that was a key component. Otherwise, you wouldn't know. I mean, you just manipulate, you're just looking at the answers and working backwards. So the fact that the sine function is an odd function, as well as many other functions we discussed, is imperative. Okay, it's important. And you will use that over and over and over in calculus. It's kind of like saying, let's just leave out even and odd in college algebra. I told you about this. That'll never work. That is too important of a construct in analysis. So now you're thinking, okay, if I'm doing a calculus problem and I have a product of sine and cosine, even though this one's redundant, I now can write them as what? Sums. And that will be an easier problem. Now you're thinking, what else could we possibly have? Well, we could have products of cosines with different arguments, and we could have products of sines with different arguments. Those would be useful. Maybe we have to integrate sine of 2x times sine of 3x. And we want to break that down into a sum. So let's do the same thing again. So now what we're going to do, ladies and gentlemen, so this one was a freebie. We're going to add 3 and 4. So we'll say 3 plus 4. And the answer is not 7. Okay, just a little humor there. Okay, so notice when we add equations 3 and 4, the sine terms absorb, but we get 2 of these. So this implies that we get 2 times cosine A cosine B equals cosine A plus B. If this were any easier, you wouldn't believe me either. These are so simple. So now we see how the algebra that we've learned all of these years, that you've learned in Algebra 1, Algebra 2, is now at play with the trig, just the same song and dance. So notice here, we can just divide by 2. So we get a product of cosine functions. Again, this is not cosine squared. This is not power reducing. This is cosine A, cosine B, where the A and B are different. Okay, this is very valuable. So this gives us 1/2 cosine A plus B. Like I say, you have to do these derivations, otherwise you wouldn't believe me. You believe me here, but these do require just a little bit of motivation. So now again, we can take the product of 2 cosine functions into the sum of cosine. Again, A and B, substitute the A and the B here, add them, substitute the A and B here, subtract them. Again, the cosine function is even, so the negatives absorb. If you get cosine of negative 2x, then that's just cosine of 2x, the negative will absorb. Continue to use the even and odd properties of sine and cosine, okay? And then for the last one, you're thinking, how could we get a product of 2 sine functions with different arguments? Now we can just subtract. So we could say 4 minus 3. 4 minus 3. And again, the answer is not 1, but we know what we're talking about now. So we're going to say, again, notice here, when we subtract, these absorb, but we'll get 2 copies of the sine. So we get 2 sine A sine B. And this will leave us with cosine A minus B minus cosine A plus B. Cosine A minus B minus cosine A plus B. So one thing I tell with the product of the sines, you start out with a bunch of minuses, minus, minus, plus. The rest are fairly user-friendly. You know, you get the plus, plus, minus. Here you get the plus, minus, minus. Here you get the plus, plus, minus. And of course, you'll think about that for a day and then it kind of fades. But that should give you some way to kind of see the subtle differences here. So now if we divide by 2, we get sine A cosine B equals 1/2 cosine A minus B minus cosine A plus B. So the key here, ladies and gentlemen, again, at this point, you'll get some practice with these, but you won't see these in the true light. You'll look at this and say, well, yeah, so what? We've got the new identity. When you get to the calculus, when you get to differential equations, when you take those of you that are future electrical engineers, when you do Fourier analysis, you'll be spending lots of time with this. And that's one of my favorite research topics. When I was a kid, I was always fascinated by Fourier series. And so the trig, the sines and the cosines, again, that turned out to be the cornerstone for the Fourier analysis, where we write functions as infinite combinations of trig functions. And that's amazing. And so I don't know, we're going to keep doing the calculus forever. Like I say, once we're gone and forgotten, everyone that follows us will continue to do the same thing. Now, the one last thing that we want to do that doesn't get nearly as much attention as this, like in Cal 1, we want to reverse these. We want to do sum to product. And you're thinking, why would we ever want to do that? Well, there are instances when that is important, okay? There are instances when you need to take a sum or a difference to a product. So we want to flip this around. So let's do that. And the change of variable is easy. I'll share that with you. So the last set will be sum to product. Now, when you look at the formula charts, you look at these and your head starts spinning. It's like, I'm never going to use these. I just want you to be familiar with them. And of course, you can always have your formula charts and your note cards to undergird you right now. But later on, you'll be good. You'll be able to write down our standard equations and work with them. But we're going to use these to move everything forward. Now, the first thing we're going to do is just a very simple change of variable that will make our life really easy. So we're going to introduce new variables. Introduce new variables. I'm going to use an alpha and a beta. And so if we're going to take these backwards, we want the sum to be represented by one variable. We want the difference to be represented by one variable to make them more user-friendly. So that's going to mean we're going to say alpha is a plus b, and beta will be a minus b. So that's going to clean up one side of the identity. And then we've got to say, okay, so what does that mean for A and B? But that's where we kind of lose sight of the fact that our equations are going to look really, really simple. So then equivalently, if you solve for A, for instance, if you add A, alpha, and beta and divide by 2, notice if you add alpha and beta, the B's absorb, but then you get 2 copies of A, so you divide by 2. So we have alpha plus beta divided by 2. Now that's not the most user-friendly argument, but it's what we're stuck with. And here you're thinking, well, how can we get rid of the A's? Well, we can just subtract alpha and beta, and that gives us 2 copies of B. So B will be alpha minus beta divided by 2. So you're thinking, wow, okay, this was supposed to make everything easier. Well, it's doable. So we've got all these new variables, and we're just going to take our previous formulas and fill them in. So use product to sum. Oh, I left out the 2. Let me put that in. Use product to sum with the new variables. Okay, so we're going to write them down. So I've got to have my cheat sheet right here. Okay, so now notice we're going to have sine alpha plus beta, cosine alpha minus beta. and then hit it with a 2. So now A plus B is alpha, A minus B is beta. So we get sine, this is a freebie, sine alpha plus sine beta will now be 2 sine alpha plus beta over 2. Make sure you see that 2. Cosine, now cosine alpha minus beta over 2. So you're thinking, these are really crazy. Now, you're not going to have as many opportunities to use these. And you're thinking, I could do an X and a Y and then X plus Y over 2, X minus Y. Use any letters you like. Okay, it doesn't matter. But now what we're seeing is that if we want to make these nice and user-friendly, we make these substitutions and then just take this. And again, the sum here, we isolate by multiplying the product by 2. That again, we have sine of alpha plus beta over 2, cosine alpha minus beta over 2. So there's our first one. Again, not something that you're going to remember. Somebody wakes you up in the middle of the night. What's the sum to product formula? Well, let me derive it. That's probably what would happen. 2, let's look at the next one. So we're going to do the same thing here. We're going to do the same setup, replace the A plus B with alpha, the A minus B with beta, same song and dance. So now this will be sine. Now we have the difference minus sine beta, sine alpha minus sine beta. This is useful in Calculus 1 when you're proving the derivative formula for sine. So there's and continuity too. So there are uses of this. There's uses, just not as many that you're going to see. Then this will be 2 cosine alpha plus beta over 2 sine alpha minus beta over 2. So let's put a box around this. So the idea here is that if you set up these identities in an order, then you can see that they're all contingent on each other. That is, the product to sum give you the sum to product. No, nothing difficult here, just it is what it is. Okay, now what we want to do is get the last two. So I'll use a new sheet of paper so we can still see it. So we go to this one. I'll just kind of expose that one right there, okay? So now the next one, again, alpha, A plus B will be alpha, A minus B will be beta. So we get cosine alpha plus cosine beta will now be 2 times cosine alpha plus beta over 2 cosine alpha minus beta over 2. So the key with this one is that we have the sum of the two sine functions. Now we have the sum of the two cosine, but we don't get the mix and match. That's the only thing. We don't get a sine. We already know what the sine and the cosine is. That was the lemma. That was at the beginning of the last section. We know A sine X plus B cosine X. We already know how to do that. That is a complicated construct. At least with this, we have a little bit more flexibility, but there, it takes a lot to move an identity forward. And so we have to be happy that we've got that lemma that I at least set up at the beginning of class. And that's when the arguments are the same for cosine and sine, but the coefficients can be all crazy, the A and the B. Now, the very last one, it doesn't get the best. I'll just say this. We don't like to write this formula with the negative here. We don't like that. We don't like to start the formula that way. So this gets run through with a negative, okay? So first what we're going to do is run a negative through. We're going to say negative sine A cosine B equals, and so when you multiply the negative, that'll just switch the order. So this is going to be cosine A plus B minus cosine A minus B. In the literature, ladies and gentlemen, this term is preferred to be first. So if you multiply this by -1, it flips the order, and of course that gets a negative. And this is the preferred way to write it. Again, convention, but I don't want you to see it written in another way and then wonder where'd that negative come from. So now this gives it to us. So we have cosine alpha minus, again, this can be used in calculus with the cosine function for continuity and derivatives. So we get cosine of alpha minus cosine of beta equals -2 sine alpha plus beta over 2 cosine alpha minus beta alpha minus beta over 2. So when you look at these particular setups here and you think about them, and here's another thing too, I got a little typo. These are both sines. These are both sines because remember when we did that. So let me fix that typo. Sine. That looked a little odd. So these are both sines. Like these are both cosines. So fix that. So when I did this, when I did the subtracting the two, we just have 2 copies of sine here. I wrote it here, but then I switched it here. So unfortunate. So that's a sine like that is, just like we have here. And then, so now we can see product to sum, sum to product. So here's a summary of them right here. So we've derived the sum to product, again, the sum of 2 sine functions, the difference of 2 sine functions, the sum of 2 cosine functions, the difference of 2 cosine functions. So again, these have the sine cosine here. These have either the cosine or all the sines. So again, the use here is limited. When I teach Calculus 1, I will use these when I work with the continuity and the differentiability of sine and cosine as alternate paths to showing that particular theory. And the main reason I do it is so the students can see the use of these identities, which don't get much airtime in calculus. But again, when you get to Fourier analysis, and those of you that move on to the university will see these again. Now what I want to do is, in closing, just do this example that you see on this particular sheet. Now, when it comes to using the sum to product and product to sum, basically you'll figure out the A and B and substitute them into the identities. I certainly don't expect you to memorize those. I showed you how you derive them, so I want you to be able to use them. Certainly you can write down the basic equations and derive them, but you're not going to get much airtime with them now. So now I want you to be familiar with them and be able to use them. Now, here's an example, just so we can see how we can utilize these new constructs. So let's see here. I've done the tangent, and then I want to do a power reducing. Yeah, well, I'll do, let's see, let me do this one first. So we've got secant of x equals 2. So these are nice numbers, but I thought it was interesting how it works out. And x is in the 4th quadrant. So the argument terminates in the 4th quadrant. And we're going to compute some double angles just to get some practice with them. These are all done the same way. Now, when we want to compute all of these, we're thinking these are all written in terms of the double angles. That is, in terms of sine and cosine. So first, what we do here is we write the triangle, the reference triangle here. This is just 2 over 1, right? So that's hypotenuse over adjacent. So we're going to write the reference triangle. So we have x and hypotenuse over adjacent. So this is like our friend. This is the unit circle, square root 3 kind of stuff. So 4 minus 1 gives us square root 3. And so now when we look at this, notice in the fourth quadrant, so in 4, cosine x is positive, sine x is less than 0. So we have that arithmetic constraint in the fourth quadrant. So now we're going to say sine 2x. Sine 2x is just 2 sine x cosine x. That's just using the double angle. And so now we can go ahead and write these down if and only if cosine x is 1/2. You know what the angle is, obviously. And then sine x is going to be what? Negative root 3 over 2. So this is stuff that we already know about. But it shows you how when we're working with any kind of number, we just follow the new identities. So this will be 2. Sine x is negative root 3 over 2. Cosine is 1/2. So now the 2's absorb. So we get negative root 3 over 2, as we would expect. And now let's do cosine of 2x. Now this is where we have some flexibility. We can just go ahead, we could do the cosine squared minus the sine squared. Let's just go ahead and use this formula, 2 cosine squared x minus 1. We have that luxury, or we could do 1 minus 2 sine squared, your choice. So now we get 2. So cosine is 1/2, so we have 1/2 quantity squared minus 1. So we get 2 times a 1/4. I'll go ahead and square that, minus a 1. So this is a 1/2 minus a 1, which is negative 1/2, of course, which we expect. And then tangent of the double angle. Okay, of course, we have a nice formula for that, but we're going to be lazy. We'll just take the ratio of sine 2x to cosine 2x. So sine 2x, cosine 2x. So we'll have, in this case, negative root 3 over 2 divided by negative 1/2. Now, when we look at this and we think about what we're doing in this particular case, the 2's absorb. And here's another thing that we want to notice here that's really very important. Let me just make a comment here. There's one thing that I want to mention here that's important. Notice, and this is very important. If we think of what's going on here, we're basically looking at these constructs as manipulations of things we already know. And so you're thinking here, we could go ahead and use the 2 tangent divided by 1 minus tangent squared. But since we're going to be lazy, we can just see that the 2's absorb, and we just get what? Root 3, which we expect. Okay? So when it comes to doing computations with the new identities, I want to show you the cases where we did the half angle and we have to basically select a plus or minus with the half angle of sine and cosine. Here, we don't have to worry about it. It's all selected for us. That is, these do not involve any pluses and minuses. But when we have the plus and minus, we have to start with what we're trying to compute and say, okay, where does this angle terminate? Okay, so we've got to select the plus or select the minus. So this is all built in. This is all built in to the actual formula. So remember, the arithmetic has not changed. When it comes to the formulas that we've developed, this is simply a manipulation of the standard identities. So when we keep thinking about how we did everything, we go back to the major set of 4 right here. This gives rise to everything. the double angle, the half angle, the sum to product, product to sum, power reducing. I mean, it's like these turned out to be kind of the magic touch that we needed to move our identities to the next level. Albeit we haven't really learned anything new, we've just learned new ways to combine things. So now we've got this nice combination of ideas here with sines and cosines, even tangents, and plus, of course, the most important one that I call the remarkable one, tangent of u over 2 or x over 2, however you want to state it, is sine of u divided by 1 plus cosine u. That you will remember. This is probably the most important formula that we've derived today, maybe only second to these. Weierstrass saw the utility of this formula when he was considering integrals of rational expressions of sine and cosine. And this is some beautiful calculus here. The thing is, we call the Weierstrass the big hammer. You only take out the big artillery when you need to solve problems that can't be solved by simpler means. And again, when you look at something this simple, you're thinking, well, we didn't have to work very hard at all. We didn't even have to draw a triangle that was difficult. And then we just used the actual deal here. So when we look at, well, here's the same example here. When we look at this, we just utilize the arithmetic that we've already set up in the problem. So what I want you to take away from today is that now we have some new ingredients to put everything together. And then for the next class, we're going to take some of these new identities and we're going to solve trig equations. And we're going to look at it algebraically, just like we do in college algebra, remembering the arithmetic of the unit circle. So I hope this has been fun. I mean, again, just remember the goal is calculus. And if you decide that you want to study even more trigonometry, go for it. We've hit all the basics, and you can just make up your own trig book and make up your own problems. But this is always fun to teach, and I hope you have enjoyed the segue into new identities so that we can solve some equations next class, and then say, see you later to trigonometry, at least momentarily, but of course, never forever, because we will use trig the rest of our lives. So you all have a great day. I appreciate your attendance today. Enjoy the nice weather. And of course, I'll send out invitations for the conference hours. So hopefully I'll see you there. Everybody take care.